Don't mess with my paper.
All right, sorry. There you go.
Hey everybody, it's Princess Coco Bananas doing differential equations. She just found her craisin. We're going to try and keep the ferret interested in what we're doing by offering her a craisin once in a while. And now she's going to walk away and eat the craisin. All right, so remember the hassle. When you have the homogeneous solution matches the forcing term, because this will go to 0 when you put it into the ordinary differential equation. So you don't get an e to the 2t survives. That's bad, because you need to have an e to the 2t. So, oh, there's a weasel in the house. Hang on, you. Would you like another craisin? There you go, right here. Hey, Weez, right there. There we go. Oh, such a good weasel. There we go. All right. Well, could you move your tail, please? Thank you. All right, so the fix actually should make sense. Suppose we don't know what the fix is. So here's f. F could be any function. Now this should make sense because this e to the 2t has to come from somewhere. So the fix has to have an e to the 2t in it. So we're trying the simplest thing I can think of, which is multiply by something. Oh, you're such a weasel. Would you like another craisin? Here you go. Here you go. There you go. Right there. Such a weasel. Now, could you move? We're trying to work here. That's good. All right, so what you do is this is the proof of why this guess works. So you have the function times e to the t, which makes it a product. So all these derivatives get complicated because you got to do product rule each time. Now, here's something that happens all the time with the Hassel guess. When you go to take from y prime to y double prime, you're going to have a match. Because I'm going to have, when I go take the derivative of this, I'm going to get an f double prime. There it is. I'm also going to get a derivative of e to the 2t, which will be a 2f prime. 2f prime e to the 2t. And then the first one of this term is going to be a 2f prime e to the 2t. So this always happens. You get a little match here. So you can always simplify like that. Combine those two terms. So what I'm going to do is I'm going to substitute these back into the ordinary differential equation at the top. I'm going to just take those derivatives and pop them back in. So here we go. I've got, I'm just writing in all the stuff that I had, and I notice that I get some stuff to cancel out. In fact, everything with just plain f in it cancels. So that leaves me only with an f double prime piece and an f prime piece. Everybody's multiplied by e to the 2t. So here's what works. Well, what if f double prime is 0? So this is gone. And then if f prime is 1, then I have an e to the 2t. So if f prime is 1, then f is t plus c. And if you have c times e to the 2t, that's the homogeneous solution. So that would go to 0 anyway. So the big deal is we'll just use t times the arbitrary constant in front, the adjustment constant in front. So there it is. That's the proof of how it works. Isn't that great? If you don't know what f would work, then the problem tells you use t. T will work. So just pretending we don't know what's going to happen still gives us what we need to have happen. Now, there's a further hassle. What if you get the repeated hassle? In other words, let's take a look at this example right here in a little bit more detail. This one right here. This has y double prime minus 2y prime plus y equals 2e to the t. Well, this is, if you look at it, this is e to the t for each root. It's a repeated root problem. And I have e to the t over here. So not only do I have the homogeneous solution matching the forcing term, it matches twice. The match happens there's two factors here. If you did the characteristic equation, it would be r minus 1 quantity squared. So r equals 1 twice. So here's the fix for that one. We have a very easy fix for you. So I'm telling you, just use t squared if the match happens twice. Just use t squared, baby. Which should make sense. It's like you're using the amount of t's you need. Now let's watch this happen, though. It's kind of cute. So here's my guess. I take my first derivative. I take my second derivative. And I just used what I showed you on the previous page, where I combined like terms here in the middle. Because you should have had two product rules, 4 terms. I have 3 terms because 2 of the terms are like terms. Then I substitute back into the ODE, which was, remember, the y double prime minus the original ODE. y double prime minus 2y prime plus y. So y double prime minus 2y prime plus y. And then I've tried to underline to show you what's going on here. These are not equal signs. The single underline shows me that my AT's all cancel out. I have 4 of them minus 4 more. And my AT squareds all cancel out. I've got a plus 1 minus 2 plus 1 more. The AT squareds all cancel out. So I'm left with 2AT equals the forcing term, 2e to the t. So in this case, a equals 1, and I'm done. I got the right answer. I've got to fix. Now let's take a look at this. Look at what actually is happening because of my educated guess. I have my educated guess, the two derivatives, and notice that I shave that t squared down to a single term with ae to the t on it. So everybody else has e to the t, but there's a t in front, either a t or a t squared. But I have one term that doesn't have a t in it, and that one survives and gives me the e to the t that I need to survive. So it's kind of cute how it happens, because you can just see the t squared, t, and then the derivative of t is 1. So there's no t on exactly one term, and that's the one that survives to give me the satisfactory guess. So the hassle, in summary, the hassle is when the forcing term matches the homogeneous solution, you multiply by t, and if that happens twice, multiply by t again. So that's a good fix for us. We're going to use it like crazy. It's going to be big. So make sure you have this idea down. So let's just quick review what's going on. You start with a differential equation where you go and do the homogeneous solution first, and you notice the match. So the homogeneous solution appears in the forcing term. So then you don't have to do this, guess what to do. You know to multiply by t. So here the guess would be, you would use, in this case, because the roots here are going to be a 2t, an e to the t, and an e to the 2t. So the hassle only happens once. So your guess would be a t e to the 2t. That would be your guess. So you do the two derivatives of this, you put them into the differential equation, and you find out what capital letter A makes the forcing term happen. And then you've fixed the hassle. And what's the full solution? What's the full solution? I'm waiting. The full solution is the homogeneous solution plus the particular solution. When you find what big A is, you now have the particular solution. So remember, your actual solution, your y, will be y sub h plus the big Y, your guess. So y sub h you get by setting this thing back to 0. Solve just this, and then finding a the way we've just done, and then you have the full solution. Now the y sub h, remember, will have arbitrary constants in it. How do you find those? I'm listening. Ah, yes, the initial conditions. So use initial conditions last. All right, ladies and gentlemen, that was a quick video. I've been sick as a dog, so you get a break. Bye-bye.